Now it's time to move to dynamical systems proper. And before we do so, before we get really stuck in with technical terms, it's worth once more pulling back, having a little bit of history. Dynamic means changing. And the consideration of change has been the one principal animating concept that gave rise to pretty much all of science, an awful lot of philosophy, and a lot of religion. When we speak of change, we're trying to understand where things come from, what constitutes identity despite change, and where everything goes. These are profound questions of the highest order. And given that we live in a world that is perpetually changing, nothing stays the same from one second to the other, the profound hope of science is that this change can be rendered intelligible, that there is some kind of order underneath this constant flux of change. This is a very, very old idea. We can go right back to the Greeks. The term logos is often used for this notion of an underlying order, whose precise form has yet to be articulated. And we go back before Plato. There was the great philosopher Parmenides. Parmenides had this wonderful mystical vision of the whole of being laid out from its beginning, from the beginning of the universe to the end of the universe, and time as not represented really, except in the spatial extension. So he spatializes time. And while his vision is profound and mystical and expressed in a beautiful poem, it leads to some odd consequences. Parmenides deduced that time was an illusion and that nothing ever changes. Now, you're welcome to that conclusion if you want. We're not going to stick with it. But his style of reasoning was very, very influential and influenced Plato and Aristotle greatly. And one of Parmenides' students was a chap called Zeno. And Zeno is best known for taking this odd standpoint and running with it and developing arguments that are extremely perplexing. These are not trivial arguments. Zeno's paradoxes are reported mostly to us through Aristotle. And here's one of them. Quoting Aristotle, "That which is in locomotion must arrive at the halfway stage before it arrives at the goal." Duh. So if the runner there, the ancient Greek runner, is running from 0 to 1, before he can ever get to 1, he has to get to a half. But before he ever gets to a half, he has to get to a quarter. And before he gets to a quarter, he has to get to an eighth, and so on infinitely, seeming to provide him with an infinity of targets and making sure he can never get anywhere at all. Here's another one. The famous race between Achilles and the Tortoise. Achilles is presumed to be faster than the tortoise in the race, so the tortoise is given a head start. Now, by the time Achilles catches up to where the tortoise was, the tortoise, of course, has moved on. He's slow, but he's not immobile. He's continuously mobile. And so the tortoise is ahead of Achilles. But we just repeat that argument. By the time Achilles catches up to where the tortoise is now, the tortoise will have moved on ahead. And so on ad infinitum, clearly demonstrating that Achilles can never overtake the tortoise, something we know to be absolute nonsense. But find the flaw in the argument, if you will. A third one, likewise from Zeno, concerns a flying arrow. Aristotle put it like this: if everything, when it occupies an equal space, is at rest at that instant of time, and if that which is in locomotion is always occupying such a space at any moment, then the flying arrow is motionless at an instant of time and at the next instant of time. But if both instants of time are taken as the same instant or continuous instant of time, then it's in motion. The point here is that if you represent the state of the arrow, you've frozen it. So if you describe its position somewhere at any given time and its position at another time, both of those are static snapshots. Time here is infinitely subdivided. And it's time that's been subdivided here, whereas it was space in the first two. But what we see here with these paradoxes is something that haunts us to this day. It's a logical puzzle of trying to use language to express both where and when something is, state, and how it changes, the dynamics. Now, these paradoxes were taken very, very seriously indeed. And the best mathematicians and logicians of the day started working on them. And they worked on them, and they worked on them, and they worked on them. And by the Renaissance, this was still a problem. Nobody had solved these problems. Nobody had figured out how to express the peculiar notion of an instantaneous rate of change. It seemed you could describe something, and you'd fixed it. Or you could describe change, but then you couldn't say where it was at any given moment. It wasn't until the birth of scientific modernity that formal tools were developed that were up to this task. And in the intervening 1500 years, 2000 years actually, this problem never went away, and it was worked on by the greatest minds of the time, and it became a political football. And people were excommunicated for coming up with the wrong answer. It was really, really tough. But around 500 years ago, scientific modernity came into being with its reconsideration of what we mean by space and what we mean by time. So Copernicus got rid of this view of the cosmos with Earth at its center. And Galileo worked on coming up with a notion of space that was infinite everywhere and always the same kind of stuff everywhere. Both space and time became featureless infinities into which the things of reality were placed. This is a scientific model. It so pervades our thinking that it's very hard to see it as such. Descartes came along and banged the big stake in at a point 0, 0, so we could have a coordinate system and say where everything was. And Isaac Newton, as we'll see, played a huge role then in developing the formal means for addressing notions of change. This is, of course, the mechanical worldview that comes into being here. A scientific framework, not a fact. It's a way of trying to render the flux of the world intelligible. And the mechanical worldview is limited. It describes the lawful motions of idealized bodies in idealized conditions. It turns out to be very useful for doing that, and turns out to be so useful that you can use it for describing the motions of real bodies in real conditions up to a point. It's no longer our best science for doing that. Well, this mechanical worldview still needed the right formal tools for describing things, and this came along in the form of the differential calculus, which appeared simultaneously, as if by magic, with the characters of Newton and Leibniz. Two completely different characters with very, very different theologies, very, very different personalities, very different sets of concerns. Leibniz argued that everything was kept going by God, and that this was the best of all possible worlds. Believe it or not, he hadn't seen 2020. Newton was an alchemist. He was intellectually quite a renegade. He didn't believe in the Trinity, and he spent a lot of his time on alchemy, as well as revolutionizing the science of optics, providing us with the differential calculus, calculating the laws of motion, and all the other stuff that Newton did. And apparently he was a very unpleasant character. The fact that the differential calculus as a formal tool should pop into being in two independent places in England and in Germany is not a miracle. I just said there was 2,000 years of people chipping away at this, of mathematicians talking to each other, trying to align their notions, recognizing that if you could get a handle on the notion of an instantaneous rate of change, you could unlock whole areas of analysis, of inquiry that were we knew should be available to us, but that weren't. At the heart of it is always actually the concept of the infinite. In order to describe instantaneous motion at a point in time, we need to make use of the notion of the infinite, and that was a difficult category. The infinite belonged to God and not to the world, as it were. This is why it caused so much trouble. So because there'd been all this work, the emergence of the formal tool of differential calculus, it was expressed differently by them, they used different notations and so on, but there had been a huge amount of preparation and collective construction. So our association of this term with those two individuals is a little fanciful. It's in hero mode as usual, the way we tell stories. The questions and the inquiry about motion and its causes, about change and its causes, were continuous throughout the entire time, and they remain so. These have not gone away. That's a little historical overview. Now, when I was learning cognitive science in the 90s in Indiana in America, most people were involved in connectionist modeling or in good old AI-fashioned modeling. But we, in Indiana University, we were beginning to use dynamics as our framework. We were starting to use the tools of dynamics for describing, for developing a vocabulary to approach the difficult questions associated with cognition and behavior. And we weren't very good at it. Some of us were better than others. And it became a much larger undertaking in the 30 years since then. But one thing that really bothered me was that it was difficult to gain entry to this as an aspiring cognitive scientist, because all the textbooks have been written for physicists and engineers, and they all were very interested in getting the calculations right, but they weren't too concerned with the concepts because they were well established. The problems that engineers addressed had to do with moving bodies or static bodies. Turns out the calculus is good for that too. So many key concepts were left undefined. It was assumed you just had ingested them, I suppose. One of the big things that puzzled me was the difference between dynamics and kinematics. And I think this slide illustrates it well. Kinematics is movement. It refers to movement. And dynamics refers to change. So what's the difference between those two if we're talking about solid objects in space, the trajectories of solid objects in space? Well, Wile E. Coyote there on the left is definitely moving, but as is quite common in cartoons, he's not particularly within the natural order. If he forgets about gravity, he's absolutely fine until he remembers about gravity, and then gravity kicks in. That's not the way things work. That's a cartoon. Kinematics describes motion, therefore, without reference to underlying causes. And so this is a kinematic description of the movement of Wile E. Coyote, and it's not bounded, luckily, by such pedantic concerns as gravity. The billiard balls on the right-hand side are also moving, but their movement is not arbitrary. They won't go off the edge of the table and hang suspended in air. Rather, the motion that unfolds here is lawful in a very precise sense. It can be made, we can understand it as arising in the mechanical domain from the interaction of forces. This is where dynamical systems cut its teeth, was in considering problems like the motion of balls on a billiard table. It has been greatly extended since then. This vocabulary becomes available for discussing very, very many kinds of problems. But at its origin, it was for discussing the movement of idealized three-dimensional objects, massive objects in idealized conditions. And under those circumstances, there's a standard way to describe something. A body is usually taken as being as if it was a sphere, as if its shape, color, texture were all irrelevant, and we could capture its position using a single point in space. So we basically reduce bodies to idealized point masses, so we can describe their position at any given time t. And then the other thing that we need to describe is their velocity, or their speed and direction at time t. Given those two, we have available to us through Newton's 3 laws of motion a set of equations that allow us to predict future states of these bodies. Of the 3 laws of motion, Newton's second law of motion has been the most important for developing predictive accounts of the motion of bodies. This is a force is equal to mass times acceleration. Acceleration is the rate of change of velocity. Velocity is the rate of change of position. These are all terms that rely on the notion of an instantaneous rate of change. So we've got position at a given moment, and we've got velocity. Velocity is like speed, but it has a direction as well. So it's not just 3 miles an hour, but it's 3 miles an hour northwest. And it provides, the framework that Newton gave us provides a deterministic account, there's no uncertainties involved, about the relation between the motions of these idealized massive bodies reduced to point masses and the forces acting on them. In fact, Newton came up with the very idea of force as the thing that holds his whole theory together, if you like. He had no idea what a force was. That vocabulary was not available. Newton often thought of forces as angels. That is something which you have to posit, but you have no blessed idea how it works. That's how weird Newton was. Now, this application to billiard ball style problems of idealized point masses in an idealized space is not anymore the only domain in which dynamics is applied. The tools developed in this context have found application everywhere. And so we use the term dynamical systems theory to refer to the suite of tools we have for describing change. And this field is as old as science itself. The name is very unfortunate. It's not a theory. A theory is a framework in which you take certain formal tools and apply them to the world and consider the match between your tools, your models, and the world. This is a set of tools. How you apply it to the world is, as usual, up to you. We saw this with the networks, where the numbers don't interpret themselves. So we shouldn't think of dynamical systems theory, which is a term that everyone uses, is not a theory. It's a mathematical framework which is suited to building theories about things. And from its initial application in the domain of mechanics and motion of bodies, solid bodies, it extended to the whole of science, of physics, of chemistry, biology, the applied sciences, the social sciences, even the dismal science of economics, which no longer lies within Logos, I assure you, uses differential equations, these formal tools that describe change over time. Those are the standard way that most scientific disciplines work. Now, science is big, there's very many formal tools, but this has been the single most influential set of mathematical concepts after counting that has ever been employed. And so it's kind of unsurprising to find it turned then to questions to do with human cognition and behavior, although the how to get purchase on that particular domain is not simply a given. So what we're going to do is we're going to introduce some basic terminology over the next few videos, learn what the jargon of the field means, and towards the end of the course we'll look at a few worked examples of the application of these tools in the field of human cognition and behavior. But they don't constitute a representative sample because many people are trying many things out at the moment. And this is definitely a great area to get into, but it's also an area in which there's plenty of room left for innovation and for novel thinking.